Thanks. I'll begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for these students and this time we have to study your creation, Lord. Just bless our work today, Lord. In your name I pray. Amen. Yes, I wanted to start with a correction to something I wrote last time. So I said that the projection onto the subspace of antisymmetric 2x2 matrices was given by this. Now we did a calculation which came to this conclusion. And the thing is, what I calculated was not the projection. In fact, it was the orth that I calculated. The orth is by definition A, B, C, D in this context minus the projection onto A2 of A, B, C, D. So in that calculation, I calculated this, and what we found that was 0, B minus C over 2, C minus B over 2, 0. So that is actually the projection right there. We found the projection onto A2 as part of the calculation, but my concluding thing was actually the orth. So let's see here. Here's the difference. The projection of a matrix onto A2 is in fact an element of A2. Right? This is itself an antisymmetric 2x2 matrix. In contrast, where is the orth? Where's this matrix? This is in where? This is in what I was calling S2, right? This is a 2x2 symmetric matrix. And of course, you can see that if we take the projection onto A2 plus the orthogonal projection onto A2, we add those operators together, we just get the identity on our 2x2. Or F2x2. The point is that the sum of these operators is identity operator, and they're related to each other, but they're different. Anyway, I described to you how we can find a formula for the projection operator in terms of an orthonormal basis for a given subspace last time. All right? Let me say a little bit more about subspaces and orthogonality, though. So one of the things I failed to say last time, and I really should, I should be over here. Definition, W1 and W2, subspaces of inner product space like this, right, are orthogonal, right, orthogonal, and we write W1 perp to W2 if and only if x1 comma x2 is equal to 0 for all x1 in W1 and x2 in W2. So this is a concept that I had not yet unfurled last time. That is annoying. Anyway, I'm going to ignore it. Sorry, guys. Is it even good music? I must not be distracted by this. I lost 2 minutes of class to this the other day. That means I'm going to have to start going 6 minutes over if we're not careful. What's that? What? Oh, what did I just do? Did that stop it? Yeah. All right, good. So this is when subspaces are perpendicular, okay? And there's a theorem that if we have W and we take the intersection with the perp of W, that these intersect at just the 0. All right? So we can also prove that the perp is a subspace. So if you give a subspace W and a subspace, the perp of the subspace in an inner product space, they're independent subspaces. They intersect at 0, like this, okay? So how do we prove that? Let X be an element of the intersection then X is in W, and X is in W perp, right? Thus, what's X with X? The inner product of X and X is, by definition of the perp, 0. Because anything in the perp is perpendicular to things in W. So by definition of W perp, this is 0. Right? But you know that the inner product of a vector with itself is 0 if and only if what? The vector is itself the 0 vector. Right? Hence what? Hence W intersect W perp is a subset of the 0 vector. And since the inner product of 0 and 0 is 0, follows, well, I don't even want to write anymore. Let me just say it follows. I mean, once you have this, it's pretty much immediate that, in fact, W intersect W perp is equal to the 0 vector. But there's more than this. In fact, W plus W perp is equal to the vector space in which you're in. All right? I mean, I proved this in the notes. And so what's that say? W and W perp are actually forming a direct sum decomposition, right? V is equal to the direct sum of a subspace and its perp. Now, the perp is also known as the, do you guys remember the definition of W perp? I haven't written that today. I'll write it again. I mean, I think I've defined it previously, but in case you forgot, W perp is V and V such that V with W is equal to 0 for all W and W. I think I might have defined this with the letter S, right? So I defined the perp even for just a subset, not necessarily a subspace, but certainly that definition also applies to a subspace. So you can prove that this is in fact a subspace, the W perp is a subspace. And not just that, it's in fact a complementary subspace to W. So we can break any vector in the vector space into something in a given subspace, and it's perp, is the theorem we have. So let me just kind of put everything together here. If W is subspace of V, which is an inner product space, then V is equal to W direct sum W perp. And so for any X in V, there exists X1 in W and X2 in W perp such that X is equal to X1 plus X2. This is a direct sum decomposition, so the choice of X1 and X2 are unique. But we can say more. We can say more than this, in fact. Moreover, the projection onto W of x is equal to what? The projection onto W perp of x is equal to what for the given in the notation I'm using on the board right now. Can you tell me what I should write there? So the projection onto W of x should be the part of x which is in the W1, which is in the W space. So that is by construction x1. The projection onto the perpendicular space, that should be the part of x which lies in W perp, which by construction is x2. Okay. So this gives us a way of looking at projection and also orthogonal projection, I mean the orth operator as I call it, without regard to a basis. You know, I haven't said anything about a basis here. I've just looked at the fact that the W and W perp are what? They're orthogonal to one another, and so they form a direct sum. Admittedly, probably to prove this involves finite dimensionality and chasing a basis. I think if you look at my proof of this in the notes, I do use a basis extension argument. So there's a gap, what I'm telling you in class. I'm not going to show you everything in class, so you should read the notes about this. But ignoring that, everything I'm doing here, you don't see a basis, do you? Right? So here's the way it works. The projection onto W is the orthogonal piece to the complementary. This is the orth, and this is the orth of W. So they're kind of, even the orthogonal and the projection operators, they're complementary in this sense. All right, enough about this. I don't think I've shown you enough examples of orthonormal bases yet, and I think it'd be healthy for us to look at an example of the Gram-Schmidt algorithm that's a little bit abstract, so let's do that. First, some just easy things. Can you guys tell me some nice examples of orthonormal bases? So just to give you a sense of where we're going today, I'm trying to round out the discussion of what does it mean for, you know, a subspace to be, what can we say about subspaces in inner product space? What can we say about the perpendicular subspace, and what theorems can we write in this context? And there's one other thing on this theorem I forgot to say, which is kind of important. The length of x squared is equal to what? The length of x1 squared plus the length of x2 squared. See that we get because these subspaces are perpendicular, which means that vectors from one and the other are perpendicular, which means we get the Pythagorean theorem, proved last time. That is going to be very important for the end of today, where we'll see least squares. All right. But before we get to that, just a little bit more about orthonormal bases. So can you give me, how about for Rn or Cn, the standard basis, right? This thing is orthonormal with respect to the usual inner products that we defined the other day, right? Either the dot product or that one that I copied down wrong from my notes and we had to fix. Yes, remember? 2, this is comforting. The lexicographic basis, the EIJ for the, is orthonormal for the usual inner product on Rn by n or Cn by n. the usual matrix unit basis. That's an orthonormal basis. That's pretty nice. Now, I want to introduce you to some weirder ones. 3. If we look at W as the span of beta, where beta is equal to the following. You've got sine of nx, you've got cosine of nx, you've got 1 over the square root of pi, that's weird, such that n is a natural number. And just to be clear, natural numbers, 1, 2, 3, 4, 5, well, we could go on. The point is that I started at 1. There are these people who are wrong, who think that it started 0. You should just not even engage them in conversation, just walk away from them. Sorry. Actually, I was doing that last year. So I hate myself from last year. But no, I don't know. Some books have n starting at 0. I'm sorry. It's the way the world is. Okay, so this, here W is orthonormal basis. I have trouble spelling. Orthonormal basis for W, which is a subspace of function space on the reals. So real valued functions of a real variable. With respect to the following inner product. Fg inner product is 1 over pi, the integral from minus pi to pi of f of x, g of x dx. What do I mean by that? I mean that you can do integrals of sine and cosine, one against the other, and they'll work out to 0, unless you're looking at sine with sine or cosine with cosine and the argument's matching. For example, if I look at the inner product of sine of nx, well, that's by definition 1 over pi, the integral from minus pi to pi, and so we get sine times sine, which is a what? Sine squared nx. What's the integral of sine squared over a full cycle? What's the integral of 1 over a full cycle? 2 pi, right? If you think about sine squared and cosine squared, they're symmetric about a whole cycle. So that stands to reason that the integral of sine squared about a whole cycle is just pi. So this integral is pi. Pi over pi, also known as 1. The same argument will show you that the integral of cosine with cosine of the same argument is 1. Well, the integral's not 1. The integral's pi, but then the 1 over pi out front normalizes it to 1. Remember that the inner product of this with itself, this by definition is what? The norm of the sine of nx. Remember our definition for norm, vector length, that's the norm of sine x squared. Remember, we're always using this definition. The induced inner product of v is the square root of the inner product of v and v. Remember that. That's where I'm getting the length comment from. All right? And you can check that if you calculate the inner product of, sine of different arguments, or cosine with sine, or sine with 1 over pi, or cosine with 1 over pi, the inner product of all those inner products are 0. So in totality, these are vectors of length 1, and the inner product of any two distinct ones is 0. In other words, that is an orthonormal set with respect to that inner product. In some sense, these functions are perpendicular and have length 1, in the sense of the geometry defined by that inner product. Another one we could do, which would probably be a good exercise, oh, by the way, while I'm at it, guys, before I get to that, can you tell me the formula for the projection onto Sn of A? What's the formula for the projection onto an of A, where here A is a n by n matrix. It's what? I'll do the first one. It's nothing more than 1/2 of A plus A transpose. That gives me the symmetric part of A. That's the projection onto Sn. There's just a stone-cold formula for it in matrix notation. I gave you A, B, C, D stuff because we could actually calculate as we did last class. But, you know, going forward, this is a nicer formula, is it not? What's the projection onto An? Same thing, but what? With a minus, yeah. You can try it. Add these together. Don't tell other professors I wrote this. What do you get? The projection onto Sn plus the projection onto An, all of that acting on A equals to A. So that says that the sum of the projection operators onto the subspaces which are complementary is the identity operator. This is not something that just accidentally happens for Sn and An. This is something that's going to be true for W and W perp, right? If you have a vector space, inner product space, and you look at the projection onto W, and you add the projection onto W perp, that is a way of decomposing the identity operator on the space into two kind of interesting geometrically based operators. That really what they do is they give you the shadow. They give you the shadow of an arbitrary vector onto that respective subspace. Projection onto Sn, what does it do? It takes a matrix and it shows you the shadow of the matrix onto Sn. Projection onto An takes a matrix, shows you the shadow of An. A matrix onto An. Okay, enough. 4, here's a weird one, P2R. In other words, the span of 1, x, and x squared, right? This one. Quadratic polynomials, possibly degenerate. And here's a little bit of a wrinkle. We're going to use inner product of f and g equal to the integral from -1 to 1 of f of x, g of x dx, okay? That's an inner product for the same reason that the integral from 0 to 1 formed an inner product. We threw that out as an example in the first day. You could change the domain of integration and the arguments still go through. So here's the kind of surprising, perhaps non-intuitive thing. That's not an orthonormal set. The monomial basis is not an orthonormal basis. Not orthonormal with respect to the given inner product. So remember that theorem and the algorithm I told you guys, the Graham-Schmidt algorithm? We can use that to take this basis and convert it to an orthonormal basis. Let's start working through that, okay? So let's, in some terms, so the set I'm starting with, let's say is, you know, U1, well, let's say V1. I forget what what was the notation I used with you guys in class for the Graham-Schmidt algorithm? What were the letters I started with, the original set? V's or U's or S's, what were they? S's, okay. So I'll stick with that just to try to S1, S2, S3, so S1 is 1, S2 is x, S3 is x squared. So first order of business is to find S1 prime prime, which I told you should be 1 over the length of S1 times S1, right? It's a unit vector in the direction of S1. So what is this? So we need to calculate what's the inner product of 1 and 1, right? Because the inner product of 1 and 1, that's the length of 1 squared with respect to this notion of inner product. All right, well that means I have to integrate from -1 to 1 of 1 times 1 dx, also known as 2, right? So what does this say? This says the length of 1, the function, constant function 1, is the square root of 2. Thus, S1 prime prime is going to be 1 over the square root of 2. So there's the first normalized vector in my orthonormal basis for P2. What do we do next? Next step, we got to calculate our S2 prime, as I called it. Oh, what did I do? I'll do better. There you go. Hey, at least I didn't poke a hole through the wall this time. I did that once. I have no regrets. I wonder if this, in fact, I wonder, is that it's too much trouble. I wonder if, like most maps, it's just covering up a hole in the wall. Let's see here. Phew, almost erased that. That was good. Okay. So next, our S2 prime, we're supposed to calculate that by S2 minus the inner product of S2 and S1 prime prime with S1 prime prime. So what this formula does is it subtracts off the piece of S2, which is in the S1 prime prime direction. So what does that mean? This means I need to calculate the inner product of, well, my S2 was what? X, and my S1 prime prime 1 over root 2 times 1. So this is 1 over the square root of 2, the integral from minus 1 to 1 of x dx. What's that give us? 0. I think. Am I wrong? What's the integral of an odd function over a symmetric interval about the origin? You're like, can't you just integrate anything plainly? Just do the integral. Right? Sorry, it's just my nature. So we just figured out that S2 prime is x because this is 0. Right? Now we need to normalize. So I need to calculate what's the inner product of x and x. So that's the integral from minus 1 to 1 of x times x, which is x squared dx, which is x cubed. See, I'm integrating. I'm doing it. I'm really doing it. And x cubed over 3 from minus 1 to 1, also known as 2/3. So therefore, the length of x is the square root of 2 over 3. Consequently, thus, my S2 prime prime is square root of 3 over 2 x. Because I have to divide by the length to normalize it, right? And dividing by square root of 2 over 3 is the same as multiplying by the square root of 3 over 2. All right, so next step in the Gram-Schmidt. I'm supposed to calculate S3 prime as S3 minus, well, S3 with S2 prime prime times S2 prime prime minus S3 with S1 prime prime times S1 prime prime. That's what the Gram-Schmidt algorithm said we should do. We should subtract off the piece of the vector which lies in the already existing directions in the basis, namely S1 prime prime and S2 prime prime. So what does this actually mean for us here? We need to calculate the integral of x squared with square root 3 over 2 x, and we need to calculate the inner product of x squared with 1 over root 2 times 1. I'll use some color coding here to help you understand what I'm doing. That's this piece. And this is that piece. We can do these integrals. They're not a big deal. What we got? Square root of 3 over 2 the integral from minus 1 to 1 of x cubed dx. Over here we get 1 over root 2, integral from minus 1 to 1 of x squared dx. The top one is 0 because we're again integrating an odd function about a symmetric interval about the origin, right? Integral of odd function, symmetric interval, 0. On the other hand, the integral of x squared from minus 1 to 1 gives me 1 over root 2, x cubed over 3, minus 1 to 1, which gives me a 2 over 3 square root of 2. Thus, S3 prime is x squared and minus 2 over 3 square root of 2 times S1 prime prime. All right, so again, this is the red thing I underlined in red. Okay, do some color coding here, make sure we understand what I'm doing. So again, this S3 was my x squared, and the S1 prime prime, I'll write here next, which was what? 1 over root 2 times 1, right? So let's see here, what is S3 prime? S3 prime for me looks like, oh, the 2's cancel, that's nice. So we get x squared minus 1/3 Now that is not a unit vector, so we have to normalize it. So let's see here, the length of S3 prime is the square root of the inner product of x squared minus 1/3 with x squared minus 1/3, right? Which is the square root of the integral from minus 1 to 1 of x squared minus 1/3 quantity squared dx, which if you tilt your head and squint, you can see is clearly the square root of 45 over 8. So, in short, what we have found, if I can summarize over here, we have a basis beta equal to 1 over root 2 square root of 3 over 2 x, and then square root of 45, well, square root of 8 over 45 rather, times x squared minus 1/3. That is an orthonormal basis with respect to the given inner product for the quadratic possibly degenerate polynomials. These kinds of polynomials are known as orthogonal polynomials. There's a vast theory of these things. These actually have a name. Up to some system of nomenclature, these are called Legendre polynomials. And that's the same Legendre you've seen in number theory. And this discussion is not disconnected from that. Although I'm not going to make the connection. All right. Great. So, there's an honest-to-goodness, gory details Gram-Schmidt calculation for you. All right. There's a website to do this for column vectors, which I'll show you in the help session when we have that tomorrow. So I'm going to turn the page now and talk to you about the least squares problem. All right? So, first of all, I just need to point out a generic picture interpretation of this theorem. The theorem I just wrote here, if we look at it, right, we can envision it in the following way. There's a subspace W, right? And if we take any old vector, right? Oh, poor choice. The worst possible vector to draw. If we take any old vector, all right, let's say x, there are two pieces to that, right? There's the part of x, which is what? Which is in the plane W, which I've called what in the theorem? I called that x1, right? But there's another part of x, which is what? Perpendicular to x1, which we call x2, and the sum of these two, tip to tail, like this. That's the piece which is, this is a right angle. These are perpendicular, right? In particular, you can notice that geometrically, x1 is closest point in W to x. If you pick any other point in W, right, besides x1, what does that do? Like, if I pick another point, like over here, say x3, oh, I'm sorry. Well, anyway, let me not get into that at the moment. It is true. I'm trying to think of how to argue that quickly here. Well, anyway, maybe I can give you an argument tomorrow in the help session. It's not particularly important that there is a proof in the notes. It's just something I get stuck on typically, and I'll come back to it. Sorry. But it is true. That is the closest point in W to x. If you shift any different which way, you're adding distance between x and that point. Oh, that's it. Look, just saying that fixed it for me. What if I go over here, this point, right? Then there's this vector right here, which is what? That would be, if this is x3, and that's x1, what are we looking at to get from here to here? Yeah, x3 minus x1, which is, by the way, what? An element of W, which means what? x3 minus x1 is what? Perpendicular to x2. So that says that the, oh, I'm sorry, I need to stop. I think I have a proof in my mind, and then when I actually try to finish it, I can't verbalize it. I'm an idiot. I'm sorry. You guys already know that. Let's go on here. So, important application to this theorem. Okay, so AX equals to B. Can we solve it? Can we solve it? Well, certainly. In fact, what is the really nice way to say when we can solve it? The really nice to say way to when we can solve it is if B is an element of the column space of A. Guess what? Then system is what? Consistent, right? That was ultimately what we understood, is that if you can build the inhomogeneous term B from a linear combination, an appropriate linear combination of the columns of A, that's when you can solve it. So if B is outside the column space of A, you're out of luck. You can't solve it, right? But what's the next best thing? So, best approximation the least squares approximation, although we tend to call it the solution, best approximation would minimize what? The length of ax minus b squared. So we'd like to make that as small as possible. That's essentially the length of the error squared. So let's think about this. We can't solve, so maybe ax equal to b. Okay, we can't solve that, but we can solve what? We can solve ax equals to the projection onto the column space of b, right? Because if we look at the projection of b onto the column space of A, that's in the column space of A, which means that this corresponding system can be solved. All right? So, well, and it turns out that that solution that you find to that one I just wrote down, that is the least squares solution. All right. Let me, I wanted to show you some actual numbers today, so let me actually put that up here. I always forget to do this, and then I regret it, but I remember today. Mm-hmm. There we go. So I'm sorry, I have muddled the closest vector argument here for you guys. It's not that complicated. I just need to actually take 5 minutes to do it and not hurry. It's my own stupid fault. But we should move on. I want to make sure I say a certain thing to you today, and if we need to repair this proof next time, I'll do it. Okay, so here's a picture of what we're trying to do. We're trying to, the column space of A is some possibly subset of Rm. B is outside the column space of A in the inconsistent case, but we can take the projection of B onto the column space. We can solve that problem, that corresponding problem. And here it is. The least, let me make it bigger. So the least squared solution, ax equals to b, is inconsistent. Then the solution of au equal to the projection onto the column space of A of b minimizes that. In other words, if I put x equal to u here, small as possible. Here's the proof. So we can take b and we can write it as a sum of the orthogonal and the projection onto the column space. All right? And then if we look at ax equal to b being inconsistent, if that's inconsistent, it means that b is not in the column space of A, right? Which, by the way, means that the orthogonal projection of b onto the column space of A is non-zero, right? There's a part of b which is not in the column space of A, which is to say that there's part of it which is perpendicular to the column space, which is to say that this is non-zero. Then, if I look at ax minus b squared, well, that's really, I just take the b and I rip it apart into this piece and that piece. The thing about this is ax. What is ax? Ax is a linear combination of columns of A, right? That's in the column space. Projection into the column space of B is in the column space. So the first two things are in the column space. The last thing is in the orthogonal complement to the column space, which means these are perpendicular vectors, which means we have the Pythagorean theorem. And so that's why I can write this length of that squared is this plus that squared. And if you want to make this as small as possible, you can't get, you're stuck with this. This is a necessary error. You can't get rid of it. It's there. But this right here, we can make as small as possible by putting x equal to u. If x is equal to u, this is 0, and that makes this as small as possible. And that's why least squares is what it is. Now, if you've studied least squares regression before, so I mean, let's just take a pause for a second here. So what I'm telling you is, so to find the least square solution, what do you have to do? You find the column space of your system, you find a basis, you run it, the Gram-Schmidt algorithm on it to find the orthonormal basis, right? And then you can construct the projection operator by taking a sum of inner products against that orthonormal basis with your column space, right? You take that, you project your inhomogeneous term B, and then you solve AU equal to B. That's the least square solution. Do you guys remember any of that from your statistics course? Probably not. You probably use software to do it, right? But we don't do it that way either, because something magical happens. Something absolutely magical happens. This calculation right here is why least squares is so beautiful. It doesn't actually require you to understand anything I just said. I could teach this to Math 221 without any of the last 2 hours of lecture, and it would still be, they could still solve the problems without understanding. Maybe you'll also fit into that camp. I don't know, but hopefully not. Hopefully not. Okay, so here it is. This is inconsistent. The solutions of the projection system are also solutions of the so-called normal equations. So here's why that is. If I have AU is equal to the projection, that's to say that B minus AU is actually B minus, well, good grief, I can't do math. So what I've done, I've subtracted both sides from B, right? So B minus AU is equal to B minus that. But this, well, this rather, is the orthogonal projection, because it's B minus the projection. That's the orth column AB. What is this saying? This is saying that B minus AU is in the perp to the column space of B. The end of last class, we derived that the perp to the column space is the null space of the transpose to the matrix. I said it for a set of vectors, but if you translate that as to what it means for the column space of a matrix, it's exactly what I do right here. The perp of the column space is the null space of the transpose of the matrix. And so to say that B minus AU is in the null space of A transpose is to say that A transpose times B minus AU is equal to 0, which is to say that A transpose AU is equal to A transpose B. Do you see any orthonormal bases or Gram-Schmidt normalization here? Not a thing to be seen. What do you see? A plain Jane matrix problem. So God has been so kind as to design math in such a way that if you can't solve a system of equations AX equal to B, and you want to find the best approximation, all you got to do is take the system, multiply by the transpose of the matrix, solve that thing, it's the best approximation. That is stupidly easy. And usually it's unique, but you need that A transpose times A is non-zero head determinant. So here's a typical least squares problem. You're given a set of data. You want to fit a linear model, right? So you got, what line has these k points on it? Well, everyone knows k points determines a line, right? No, 2 points determine a line. If you've got 3 or 4 or 5 or 6, there's no guarantee there's a line that has all those points, right? So it's probably an inconsistent system. So your inconsistent system, when you plug it in, looks like this. To solve it, you just multiply by the transpose of that matrix, and that gives you the least square solution. Here's an actual example with numbers. So to find the line closest to the set of 4 points like that, I shove these points into my linear system. It gives me this matrix problem. I multiply by the transpose of the matrix to find the so-called normal, the normal equation. This is 2 by 2, so I can multiply by the inverse to solve it. Wham, bam, and there's your best fit line, 0.6x plus 1.6. That's the line which is closest to this data set. But you can do this for any linear model. You can do it for a plane. I can have a set of points and ask the question, what plane is closest to a set of points? Right? Everybody knows that you can find a plane that goes through 5 points. No, you can't. 3 points determine a plane, right? 5 points shouldn't, but you could find the plane which is closest to these 5 points by least squares, and that's what I do here. So I take the plane is the graph of x and y, like this. This is a linear model for the plane. I plug my data into the linear model. That gives me a system of linear equations, which is overdetermined and hence inconsistent. I multiply by the transpose of the matrix for the system. That gives me the normal equations. I solve the normal equations. I get this. There you go. That's the best fit plane. to those given. That's the plane which is closest to those 5 points. It's kind of cool, right? You can also talk about models where you have nonlinear functions as long as the parameters appear linearly. You just plug in the data. It gives you a set of linear equations in the parameters. Again, you can solve it. So here I find the best fit parabola using this method. But finally, just, I know we're about out of time. You can also linearize nonlinear systems to use least squares if you want. Here is an application of the calculation I did today. So, if you're working in like P2, we don't have matrices, unfortunately. We don't have the normal equations. Wah. But if we already have normalized a basis like we did today, we could use that to find the projection, for example, of the exponential into P2. The quadratic polynomial, which is closest to the exponential function, you can take the projection using the Legendre polynomials I did today. When you do that, this is the quadratic which is best approximating the exponential into the sense of least squares. And finally, the other thing I showed you, this basis, the cosines and sines, that is the start of what's called Fourier analysis. If you take now here we leave the realm of linear algebra, because if we could take infinitely many components, we could do things like try to build this square wave using a sums of sines and cosines. The way we do it is we take the projection of this function onto the sines and cosine directions, take the sum of infinitely many of them using what are called Fourier coefficients. They're actually integrals. And when we do that, it produces pictures like this. But this is just the infinite dimensional extension of what we're doing. This is called Fourier analysis. There's a little bit more here than just plain linear algebra because we have to deal with convergence of sums and stuff, but it's very much part of the same story. The way that we rip apart music into its notes, that kind of compression, I think MP3 is based on this idea. That's actually infinite dimensional least squares. So anyway, I'll shut up. Enough show and tell for today.